So now it's recording. Yeah, recorded videos are important for you when you work on the homework assignments, I believe. So let's see what we have for this week. There's one homework assignment due next Monday. The first one, estimate delay at the output. This is exactly what we did on Monday. So I'm going to upload the notes. I'm sorry the video is not available, but I have the notes. So all of you are here, which is good. Okay. Draw the resistive capacitive digital model of the one pair of inverters. We covered partially on Monday, and today we'll finish the topic, so you are good for this one. And what is the dynamic power dissipation? Yeah, we'll do this today. That's it, pretty simple. Okay. All right, let's get into the topic. I think we were here talking about the digital model for the inverter. These are the caps. Okay. Then we are able to draw the digital model this way. So this is Cin, the input capacitance of the PMOS, which is 3/2 of COXP, right? And this is Cin, which is 3/2 of COXN. This is Rn, this is Rp, and this is COXP, COXN. So if you look into this input, right? So the overall Cin equals Cn plus Cnp, so which is 3/2 of COXP plus 3/2 of COXN, which is 3/2 of COXP plus COXN. Very simple. So TPHL as the output, this is V out, is what? TPHL is H to L. So it was L, was low, but at the moment it's getting turned on. Sorry. It was H to L. H to L means it's being put down to ground. So this resistor is getting engaged, and the two capacitors are getting engaged as well, because this is a DC source, which is the AC ground. So you have to rotate it and short it to ground. So you have two parallel capacitors, and this is the resistor getting engaged. There's a channel resistance of the NMOS, and this is off because it's H to L. Okay, so it's being put down to ground. So TPHL equals 0.7 Rn, right? And COXN plus COXP. TPLH is being put up to VDD, so RP is engaged, so it's 0.7 RP times COXN plus COXP. Any questions by far? It's clear? Okay, it's a quick review from what we covered at the end of the lecture on Monday. Okay, this is just a one inverter. It's just one inverter, right? Input, output, input, output. A lot of times in digital circuits, you have buffers and have a lot of resistors to be put in series or in the ring, right? So it looks like this, which makes the situation more complicated. If you look at the node in the middle, you have to start drawing the model because the output of the first one is connected to the input of the second one, right? So that's the first one. It's directly shorted to the second one. This is the same node here. Oh. Okay. So what is the capacitance at this point in the middle? The DC sources are AC grounds, so you rotate them and short it to the ground. So we got 4 capacitors in parallel. And these are the output capacitors, which engage in the mirror effect, right? So this is COX P, COX N. What is this? Yes, 3/2. So C total equals 5/2 of COXP plus COXN, right? So add these two together, and factor 5/2 out and put them in addition in parentheses. So if you have 4 of them in series or in a ring like this, what's going to happen? It's going to do nothing. So after we analyze the time delay of the ring oscillator or the frequency of the ring oscillator, we'll come back to this topic. But now this is not going to do anything. It's just a latch. So we'll talk about why it's a latch later, okay? Later this lecture. But this is not going to oscillate. Why? If you have at the moment, you have voltage, for example, it's from low to high, okay? At the moment, okay? So it becomes a logic 1, logic high. It's being inverted, 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 inverted. Still the same signal. It's not changing the shape. Still itself. So it's not going to oscillate. All the signals at each node is very stable. So it's performed like a latch. So it's not going to oscillate at all. I was drawing this low to high, trying to show you the behavior here, but actually it won't happen. If it stays at the 5 volts, and this will stay at 0 volts. This will stay at 5 volts. It will stay at 0 volts. It will stay at 5 volts. It's a DC voltage, and here's a line, and at the end, it's also a line. So it's going to keep staying at a line at 5 volts. It's not changing. Okay. So if you have an odd number of inverters being put in a ring like that, it will change the story. We'll put 5. So for example, at a moment, you had a signal like this over here, right? This is 5 volts. It's going to invert it, invert it, invert it, invert it, and invert it. What's happening? Yeah, so here, from low to high, it's 5 volts, right? But after 5 inverters, it becomes 0 volts. If you look at this node and this node, it's the same wire, it's the same node. What's happening? Yeah, it is, yeah. So if you just look at the signal here, right? I got this over here. And if you look at this signal, it's getting delayed, right? Getting delayed. And eventually, at the end, it becomes this. So what's happening? If you, it's just the voltage, right? You connect them together, it becomes a little pulse. You get it? So whenever, so this is from low to high, right? But after a while, it goes back to 0, okay? And then this one will be delayed at the same way as whatever the 5 volts is getting delayed. So it's being delayed through all the inverters, and eventually it will go up, and then it will be delayed and will go down, and delayed, go up. So what's happening? It's oscillating, right? It's not stable. It doesn't like the even number of inverters in the ring. It's very stable. It's a latch. But this one is not. It's oscillating. It's not stable. And a lot of times you do need put an odd number of inverters in a ring like this in the digital circuits, because you can create a super tiny oscillator. Remember, in microcontrollers we had all these crystal oscillators on the board. It's huge. But just use the inverters, for example, like the 5 nanometer technology. It's just in nanometer level, and you put them like in a number of inverters in the ring, it will create a signal, a clock. A lot of times it can be very accurate, depends on the calculation. So now let's look at this, how we calculate it, how we calculate the clock frequency. If we are using this as a clock, we do need the frequency. We do need to know the frequency of it, right? So how do we calculate it? So at this node, if you are having an example of from high to low, right? High to low. So at this node, there will be a time delay called TPHL. You agree with that? And here will be a little delay. The name of the delay is TPLH. And you can calculate it based on the model we built over here. So now you know why building the model is important, because you are able to calculate the time delay of a functional circuit. It's being used for a lot of things. And this will be another TPHL. There will be a TPLH. And this will be a, wait, so it'll be a TPHL. Okay. This is just for this pulse. If you count, if you have another example, like we have this, right, for the other half of the period. Okay, so it's going to form a 0 volts, 50% of the period. So it's going to have another set of all these time delays. So if you count over here, how many TPHL do you have? 1, 2, 3. So if you count the other half of the period, you are having 1 HL, 1 HL, right? So 2 more HLs. So if you add them together, you are having 5 TPHLs. And same to the other one. So I have 5 TPLH as well. So if you add them together, this form a one period of the square wave. So one period means it has 5 volts and a low and a 0 volts involved, right? So this is one period. So this is T. If you know T, you know the frequency, right? Frequency equals 1 over T, which is 1 over 5 TPHL plus TPLH. So we are assuming all the inverters are equivalent. So all the TPHL are equal. All the TPLH are equal as well. So you can calculate the frequency of the ring oscillator by using this equation. And you can find the model, the numbers from the model. What are the CUX? What are the R and the RPs for the calculation? That's the frequency of the oscillation. And this will be the number of the inverters. So it's N, right? So we can generalize the equation as N times TPHL plus TPLH. It must be an odd number of inverters in the circuit in order to oscillate it. So if you need a lower frequency, you want to oscillate it slower. Do you need the more inverters or do you need the less inverters? You want to oscillate it. You want a slower clock. Yeah, you need more because you got more inverters, got more delay. More delay will make the periods longer. The T will become longer. Then 1 over T will be smaller, right? So the frequency will be smaller. I was that was many years ago. I was reading some of the papers. People are making a super fast camera. They design a camera chip, and what is that called? A shutter. They want to make the shutter being activated with a super sharp pulse, and it's very difficult to generate that sharp clock or pulse using oscillator on the board, like even the 100 megahertz. It's still not as fast as these ones. So they built a ring oscillator on the circuit to turn on the camera really quickly in order to capture a really fast signal, like optical signal. So that's how they design a high-speed camera using ring oscillators to control the shutter. Okay. I think there's an example. Calculate the oscillation frequency of a 11-stage ring oscillator. And these are the parameters. NMOS Rn equals 3.4K. These are all from the textbook. Okay. CUXN equals 0.625 femtofarads. Rp equals 0.4 kilo. CUXP equals 1.25 femtofarad. So what is the frequency? Since we know it equals N times TPHL plus TPLH. And TPHL equals 0.71. Yeah. Good. TPLH equals, it's being pulled up. So the PMOS is engaged, 0.7 RP. Still the same caps, right? Make sense? Any questions? You're good? Dynamic power dissipation, very simple equation. That's a capacitive load. And here's the VDD of the inverter. That's a ground. All the digital circuits can be modeled this way. There are other logic gates, but they're all driving some capacitive load. So it's charging and discharging the cap. The average current running into the or being consumed by the capacitor with charging and discharging it equals Q total, the total charge, the charges, divided by the frequency, divided by T period of the signal, which is VDD times C total over T, because V times C is Q, right? So you need to remember this as an electrical engineer. So V times C is Q. And so power, the average power consumed by this node, okay, equals the average current times VD. So VI equals P. Power equals V times I. That becomes VDD square if you plug this, substitute I average with this one. So it becomes VD square times C total over T. And 1 over T is F. So this becomes VDD squared times C total times F. Okay. You don't have to remember the equation, but you need to know that the power consumption of digital circuit is related to what? Clock frequency, yeah. Capacitance, right? Every word has parasitic capacitors. Capacitance is driving. And VDD. So it must be, you probably you saw all different voltages, like 5 volts, sometimes 3.3 volts. And a lot of transistors are running at 1 volt. You probably don't know that. So most of the 180 nanometer from TSMC are able to be driven by 1 volt VDD. It's amazing. So why did all the engineers spend so much effort to reduce the VDD for the circuit? Because it's lower consumption, lower power consumption, right? So if you can use 1 volt, don't use 3.0 volts. Even though you connect the 3.0 volts to the microcontroller, if the microcontroller is under 180 nanometer technology with TSMC, it has a on-chip regulator. LDO, LDR. I might be wrong. I forgot. I think it's LDO, but I don't know what it all stands for. So anyway, so it's called low dropout regulator. It's a voltage regulator being put in the chip. Instead of the regulator you have been using for microcontrollers, right? The 3.0 or 5 volts regulators, you can solder on the PCB. So these are voltage regulators that people put in the IC chip. So directly connect this one to the power input. So the CPU, for example, this is the chip, and the CPU most of the time is running at 1 volt. Even though you have a 3.0 volt power supply for the chip, but eventually it's being regulated by a regulator and feeding 1 volt to the CPU. And this needs to be low dropout voltage because the dropout voltage is loss of the voltage after the regulator. If you have a 3.0, for example, the 3.0, let's see, the 5 volts regulator we have been using, the 1 amp version, I think the dropout voltage is somewhere around 600 millivolts. So should you put a 5 volts at the input for that regulator? The one looks like this, okay, remember? Okay. These are like 10 cent, super cheap 10 cent regulators. Not really advanced, okay? So what's the minimum voltage you should give to it in order to regulate it to 5 volts output? Yeah, 5.6 is the minimum, right, in theory, but usually we don't do that. But it accepts voltage usually from, I think from 6 volts to 12 volts. That's what you can see on the data sheet. Okay, it won't be lower than 5.6. So never put a 5 volts at the input to the regulator because it won't work properly. That's the dropout voltage. And for the horseshoe project we did in microcontrollers, if I remember that, I have limited space on the horseshoe, so I can only put 1 battery cell and I have to pick up a really tiny battery for that design. So one LiPo battery cell is how much volt? One LiPo battery, what's the voltage of one cell of LiPo battery? You should know that actually because it's really hands-on. 3.7 volts. Okay, so 3.7 volts for each LiPo battery cell. And you can see some of the LiPo battery cells, it has 11 point, like a 12, I forgot the value or the rating of it. But usually it's 11.7, I think. That's the voltage rating of it. This standardizes, you know what I mean? So LiPo batteries, it's 1 cell, 2 cells, 3 cells. They standardize it. It's multiples of 3.7. So if it is like 11 point something or 12.1 volt or 11 point something volt, okay, I forgot the exact value. How many cells are in there? 3, right? It's just 3 cell LiPo battery. I can definitely find a 2 cell LiPo battery which give me 7.4 volts. It's really nice. A lot of times we use remember the big blue chargeable battery in the lab? That's 1 cell. So some of the cells are bigger, some of the cells are smaller, but they are all standard cells. So the standard voltages. That's 1 cell is 3.7 volts. If you connect 2 in series together, you're getting 7.4 volts. It's really nice. So we have been using this one as an input for the 5 volt regulator a lot, which works perfectly. Okay. However, for the horseshoe project, I don't have space for a 2 cell battery. I can only put 1 cell LiPo battery in there, which is available. You can buy it from Amazon, any other vendors. That's only providing 3.7 volts. So the ESD30 tools are receiving a 3.3 volts at the VDD, right? So the room is tiny. It's only like 400 millivolts in theory. Sometimes the battery is getting weaker, so the gap can be smaller. So if the gap between the battery's rated voltage and the voltage required for the microcontroller, if the gap is small, are you having more troubles or less troubles? Huh? If the battery's rated voltage is very close to the required voltage of the microcontroller, are you having a lot of troubles or having less troubles? Hmm? No, you have more troubles. And closer, which means you have to find a regulator that you cannot directly power it up, right? You cannot just use a battery to power it up. There are a lot of ripples and it's not working. You need the regulators in between the battery and the microcontroller. That's what you learn from MATLAB, right? This that's a design you should follow all the time. You need regulators. So the battery cell is only 3.7 volts, and sometimes when it's getting weak, it's lower than that. Okay, but it has to be after the regulator. It has to be 3.3 volts. So it has a pretty um, tough requirement for the regulator. If you look at the regulator's dropout voltage, it cannot be more than 400 millivolts. But if you look at this one, you definitely cannot use this one. This one is going to drop 600 millivolts no matter what. You can find a 3.3 volts regulator, the 10-cent version, right? The cheap one. But it's dropping 600 millivolts. So this one, if you drop 600 millivolts, in theory, you're only getting 3.1 volts. If you're losing some of the voltage for the battery, it's getting lower, so it's going to be below 3 volts. You're getting issues powered up. Okay, so you have to pick up a high quality regulator. So I was able to find that one. If you go back to the tutorial in that class, it's a super tiny chip. It's probably the same size as this little mark on the paper. And very difficult to solder on the board, but it works really, really well. I think the dropout voltage is only like 200 or 100 millivolts, which is amazing, like only 0.2 volt loss. All right. Okay, so remember this term, low dropout voltage or dropout voltage. What is dropout voltage? It's not you drop out from the class or the college. Dropout voltage is a loss of the regulator. No, it's a complicated circuit, I have to say. So it's like the voltage is input. You never reach the rails of the voltage, like the ADC, for example. I think you brought up the ADC, remember? So it's never reaching the rails. You're having loss from the G2, D2G or G2D. There are losses from the two rails. It's never reaching the two rails. Okay, now let's look at the clocked circuits. Before we do that, we should look at the latch first. So at the beginning of the lecture, we talk about the latch. So if you have a 5 volts, for example, at the very beginning, okay, when the switch is closed, it's just a one simple inverter. If you open the switch at a moment, so when the switch is closed, you have 5 volts at the input. What's the output of the inverter? If the switch is closed, right? 5 volts is the input. What's the output? 0 volts, right? Okay. You don't have any output. You don't have any connection after this inverter. So if you at a moment you open the switch, okay, open it. So what's happening to this 0 volts? No, you open it. So nothing. So nothing doesn't mean 0 volts. It's a floating wire. It's a floating wire. It's not a strong ground. Like an inverter, if you don't put anything to the input, are you getting a 5 volts? That's a good question, actually. Just grab an inverter from the lab, right? Grab an inverter from the lab, and you plug it into the breadboard, and and powered up and grounded, right? If you don't put anything over here, are you getting a 5 volts? If you're thinking there's nothing 0 volts. It's a very good question, actually. So what is nothing? Is nothing 0? So nothing is just a piece of metal, right? It could accumulate some charges, depends on the environment, the humidity, and whatever the charges on your finger. When you grab it, it may accumulate some charges, but definitely it's not 0. 0 means it's a solid ground. No matter what you connect to it, it's gonna discharge it to ground. So nothing is not ground. Okay. So it's unpredictable. You cannot say it's definitely going to be 5 volts. It may be 5 volts if you have a pretty low voltage at some moment. You may have the PMOS on. Could be, right? It's possible, but it won't stay long. So it's unpredictable. It's not 5 volts, not 0 volts. It's just nothing. Sometimes you measure it. It could be like just in the middle, like 2.5 volts or 2.6 volts. It's just nothing. You couldn't determine it. Okay. But because this is open loop, the 0 volts, it won't be 0 volts after you turn on open the switch, which means you don't have any voltage connect to it anymore. It was the 0 volts, like 0 volts potential being stored in all these caps, right? But because you don't have any energy input to keep this voltage stable, so eventually it will become unpredictable again, like this one. You don't have any input. It won't be 0 volts anymore. It could be like 0.8 volts, like 0.9 volts. It's changing, depends on the environment, but it won't be 0 volts anymore. However, if you give a 5 volts to it, the NMOS is on, it's going to pull this down to ground. It's going to be a really solid 0 volts. You know what I mean? So it's going to change depends on the environment. So if you had a 0 volts when it's closed, right, at the 0 volts at the very beginning, it's going to turn on the PMOS and it's going to pull this point up to 5 volts to the VDD. And at some moment you disconnect it, same thing as what we did for the 5 volts, it disconnected. Are you going to have this 5 volts staying here for forever? You are saying, hey, we have parasitic capacitors, right? So they will be able to hold the 5 volts, the charge, for over there. It's going to be a floating 5 volts. That is right. It's going to hold it for a little bit. Eventually, it will be discharged to the environment. Okay, to anywhere on the circuit, wherever this is plugged into, or the air, or anywhere, it will be dissipated. And also, the transistors are not perfect, so it's going to leak current to the ground. So eventually, this will become unpredictable as well. So which means if you have just an inverter, this point won't be able to store the charge or store that voltage forever. So what if you have this circuit? It's like the even number of inverters to form a ring oscillator, but it's not oscillating. So it's the latch. This is the latch. So why is this the latch? If there was a switch as an input, could be 5 volts, could be 0 volts. At a moment you open the switch to disconnect from any input source. If you had a 0 here, it's an inverter definitely because it's powered up. Inverter is working, right? So this becomes 5 volts, and after another inverter becomes 0 volts. So it's stable, it's not changing. input. So be fed back to the input, it's still 0 volts, it's stable. It's going to stay there. However, my question is, are these voltages, like this one, are they stable? Are they going to be dissipated or being discharged by something and become unpredictable? Mm-hmm. That's right. So it's not floating voltage. Okay. As long as the power for these ones. Okay. As long as you power it up and ground it, it's going to be stable. So if you look at the transistors, okay, this one on if you have 0 volts. So this one, this is on, right? This is on. 0 volts, this PMOS is on. And 5 volts, this NMOS is on. So you got PMOS and NMOS on at the same time. Are they competing with each other? One is pulling this node to VDD, one is pulling it to ground. Are they competing with each other? Why? Yeah. This is a joke, right? So we are looking at, this is a channel, but here is a gate. It's not a channel. Okay. So it's stable, it's a latch. Sometimes you will see this circuit being drawn this way. And the difference, same circuit. Just trying to confuse you. Okay, so now you know what a latch looks like by using inverters. So we can form a level sensitive latch. So D is here. That's a transmission gate. PMOS, NMOS. Pay attention to here. So the PMOS signals are getting inverted. So if this transmission gate is on, this is off. If this is off, this is on. And here's Q. Are familiar with that? Right. This is Q now. This is Q. So why is this the latch? The transmission gate is just a switch. Right? If you turn this on, you're actually making connection from here to here, and it forms a latch. As the latch we just introduced over here, right? It's just two inverters in a ring. It's like this one. It's like a register, right? The latch is going to store the voltage there permanently, as long as you keep it powered up and grounded. So why is the level sensitive latch? Remember we learned that, I think that's a NAND gate version of the SR latch, or the level triggered SR flip-flop, remember? So it's performing in a very similar way. And why it works that way. So this clock is connected to the NMOS. So if clock is 1, if clock is 1, what's going to happen? So this is on, right? D will pass this transmission gain and arrives Q naught. And also, it's going to arrive Q as well, being inverted and arrives Q. So D is Q because it's being inverted twice. So D is exactly duplicating, Q is duplicating D when clock is on, right? Because it's just a switch. So when clock is on, what's happening to this guy? It's off. But is that affecting Q? Is that going to affect the Q at all? If this is off, is it going to affect Q? No, Q is just the output of the inverter, right? This is after the inverter. If I'm using this as a latch, Q is readily available whenever the clock is on. And also Q is going to follow D. If D changes, Q will follow it. Make sense? That's why it's level sensitive. It's level trigger. It's not edge triggered, which is not ideal. A lot of times we're going to use level trigger, which is not tolerant to the changes of the data, which may happen. Okay. So what is this one doing though? So when clock is on, D will pass this gate, this gate, this gate, and arrives Q and Q naught. No problem. So when clock is low, what's going to happen? So this will be off, right? And this will be on. So what is this circuit doing when clock is low? It's a memory, right? So can we form a edge triggered version of it instead of using a level trigger since we don't like it? So these two transmission gates have the same clock, and these two have the same clock as well. And here's Q naught, and this is Q. Is this going to do a edge trigger flip-flop? So when clock is low, for example, when clock is low, so what does clock bar mean? It's inverting clock, right? It's inverting the clock signal. So when clock is low, clock bar is 1. So this NMOS is on. and this PMOS is on as well. So this is on, right? And this is also on. These two are off. So if this is off, it's preventing this signal getting from getting through this gate and arrives here, right? So when clock is low, it latches or it stores the value in the latch here. So when clock is high, so when clock is low, it stores the data over here, and also it passes D and store it here temporarily, right? When clock is low, this will arrive here. At the rising edge, this is turned on. This is turned on, so D will pass this transmission gate and these two gates and arrives here. So at the rising edge, D will be sent to Q. So why do we have to turn this on when D is being sent to Q? See, when this is on as well. They have the same signal. Right? Why do we want to do that? You see this memory state, right? Yeah, so D will be stable here, right? So D is being stored over here, it's not changing. Whenever it's being sent to Q, the rising edge is not changing anything here, so D will be stored over here. So we also want to turn off this guy. I'll turn off this guy because we want the new Ds. That's a D being stored from the last falling edge. I'm going to store it here, and while it's being sent to here is stable D. It's a very stable D being sent to Q and Q naught. Okay. Is this a rising edge trigger or low or falling edge triggered? So when we're talking about the triggered, I think we are saying when it's being sent to Q, right? So if that's a rule, okay, is it rising triggered or falling edge triggered? Rising edge triggered or falling edge triggered? When D is being sent to Q, which edge? Rising edge. Falling edge will store D temporarily in the middle, and the rising edge will send it to Q and Q naught, right? Okay, so Friday will be the last lecture. We'll talk about some of the memory circuits and finish the analysis of this circuit as well. And next week will be just the labs. You guys work on your project and the whole assignments. Okay. All right.